This is Monet Sherman. I'm going to be presenting to you my lab report for constant motion, Lab 1. So in this presentation, I'll be discussing first the lab introduction, and then some observations and the corresponding code modifications I made to the starter code. And then we'll observe the observed data versus computational model before getting into our conclusion. This lab is founded on the principle of Newton's laws of motions. First, with Newton's first law of motion, the principle known as inertia, that an object will not change its motion unless acted on by an unbalanced force. And Newton's second law of motion, which simply put is F equals ma. Acceleration is directly proportional to force and inversely related to the mass of an object, but it can also be put as the derivative of momentum. Some other important equations that we'll be using in this experiment are velocity equals position, change in position over change in time, and final position equals initial position plus velocity times the change in time. In this lab, we aim to demonstrate the principle of Newton's second law by observing an object in constant motion, in a way verifying the accuracy of this principle by comparing observed real-life data to a theoretical computational model. To start off this lab, import a video of constant motion to the tracker software and make all the according changes in order to collect the data shown here. And in GlowScript, create a computational model by manipulating the starter code to reflect the video analysis results. Lastly, we'll create a position versus time graph featuring data from both models and compare them. Here are my video analysis results. We see that time takes place between 0 seconds and 2.33 seconds, and the initial velocity we obtained was 0.483 meters per second using this formula. My changes to the starter code are underlined here in red, starting with some empirical data that we collected, the initial velocity and the ball mass. And another important change was changing FNet to vector 0, 0, 0 to reflect that since constant motion is going on, there is no net force acting on the system. Lastly, I changed ball position formula to be the initial ball position plus ball velocity times delta t to reflect this here equation. Here are the graphs created from GlowScript and Tracker respectively. And here is the data from both experiments laid on top of each other, both the experiment position and the model position. We can see they're fairly similar and diverge more towards the end. And to get into why, some potential sources of error could be the camera angle possibly distorting the video, thus not capturing the exact motion. And we also cannot ensure that there was no friction acting on the motion with complete certainty, meaning in practice, the FNet could actually not be 0. What if the positive and negative x directions were switched? If this happened, the data would be flipped, so to speak, and the slope would be negated, though the values would be the same in magnitude. The computational model predicts the actual motion fairly well. It's not realistic to measure all the forces acting on an object and add them together, as countless objects exert very small gravitational force on one another constantly. That concludes my lab report. Thank you.